Okay, so today we're going to be looking at flapping to equality. This question can be posed in various different ways. This is the normal way you'll get it posed, but ultimately what this includes is dissymmetry of lift, flapping to equality, and flat back. So quite important to understand, because actually anytime you transition into forward flight, or even if you're sitting in the hover with significant wind or not, actually you're going to be experiencing some of these effects, and you'll have to put control inputs most of the time to actually stop it or prevent it. So if you understand this, it will make you a more proactive pilot and ultimately better, hopefully. Okay, so there we go. That's the drawings that you can do. You don't need to have a perfect circle or anything like that. You can literally just use blades, as long as you make it clear which way you are rotating. In this particular example, I'm going to use a counter-rotating head for a helicopter looking down from the top. Two diagrams, they can just be identical diagrams. I've put an additional rotational velocity on this side just for now, just to help later, partly out of mistake. So where do we start then? So first of all, we're assuming we're in the hover here. There's no external factors, no wind whatsoever, and we're sitting comfortably in the hover, pulling pitch. So what happens now if we start to move the aircraft forward or experience some kind of wind from the front? So we'll assume the aircraft is moving in this direction, and therefore it's going to be generating an airflow. So the first thing before we get started is that we know that this blade is going to be rotating at the same speed as this blade in the hover. So we can assume that VR, which is the rotation velocity at this point, is exactly the same as the rotating velocity at this point. So at the 3 and 9 o'clock position, we've got the same speed. As soon as we start to move forward and we generate an airflow from the front, let's call it VW, we are now increasing the airflow across the blades, but not all of them. So let's start on the advancing side then. So on the advancing side, we've got the rotating velocity, VR, and we've now got an increased airflow coming down against it, which is going to increase that relative airflow. So we end up with VR plus VW at this point on that blade. Conversely, on the other side, we've got VR, which is the rotating velocity in this direction, but we've also now got an additional velocity going in this direction. So that's going to cancel out some of the airflow that we've managed to create over that blade. So the resultant airflow, resultant relative velocity over this blade is going to be VR minus VW. So how does that affect? Well, looking at the lift equation for this particular side, we've got a increase in velocity. And if we've got an increase in velocity on this side, we must therefore have an increase in lift. So on this side of the blade, where we are gradually increasing our exposure, or we're pushing this advancing blade towards the oncoming wind, we're going to get an increase in lift. On the rotating side, conversely, we're going to be moving the blade away from the advancing airflow, and therefore we're going to get a reduction in velocity, which is going to give us a reduction in lift. Therefore, we're going to end up in a situation where we've got more lift on the advancing side than the retreating side, and that is the first stage we get to, which is called dissymmetry of lift. So we've literally got a dividing line down the middle where we've got a different amount of lift on each side. So if we imagine we've got a very basic helicopter with a completely fixed head, ultimately what's going to happen if we've got more lift on one side than the other, then the aircraft is just going to roll. As soon as we start moving forwards, the aircraft is just going to keep rolling around to the left in this case, and we're going to need to put continuous right cyclic in order to counteract that. That's not exactly what happens though, and so a lot of aircraft, they will have a flapping hinge or an articulated head, and what that means is the blade can actually flap in reaction to this increase in lift. So how does that actually help us? So if we look at this blade, and we'll imagine this is the aft blade, the one in the 6 o'clock. So let's start with how the lift changes. So at the 6 o'clock point, we've got no aspect of this wind velocity acting on the lifting edge or the leading edge of this aerofoil. As soon as we start to move it through the 6 o'clock, we're starting to expose a little bit more of this blade to the airflow. So we're going to start getting an increase in lift in comparison to the lift at the 6 o'clock point. As we continue to move it forward, you can see the profile increases and we get more and more exposure to that oncoming airflow, which means our lift is going to continue to increase. And because we're getting more and more exposure to it, it's going to be an acceleration of lifts. So the further around here, the higher and higher this lift force is going to be, and therefore at first, because we've got a flapping hinge on this, it's going to start to lift up because we've got more lift. But as we go round more and more, because we're getting more and more lift, it's going to flap up even quicker. And the speed at which it flaps up is going to increase more and more until we get to the 3 o'clock point. At this point, we're now going to start moving through the wind velocity and start to reduce that profile of the blade. So the blade is still going to be flapping up, but it's not going to be flapping up as quick. And the speed at which it flaps up is going to reduce more and more and more until we get to the 12 o'clock point. So we can see that the max rate of flapping up, or the fastest acceleration of flapping up, is going to be at the 3 o'clock point. What does that all mean in terms of the flapping to equality? Well, as we come through, we've talked about the fact that it's flapping up, or as it flaps up, we can see with a blade, as we flap it up, we are basically inducing a vertical component of airflow coming down through the disc. So this static air above is now being effectively pushed down through the disc because the disc is coming, the blade is coming up through it. What does that mean? Well, a vertical airflow coming down through the disc, we know from all the various principles of flight as an induced flow. So as we come further around towards the 3 o'clock, we're going to get a gradually increasing amount of induced flow coming down. So if we've got an increase of induced flow, you can see that we've got a much steeper relative airflow, which is giving us a smaller angle of attack. Smaller angle of attack gives us a smaller coefficient of lift. So if we've got a smaller coefficient of lift, that's going to reduce our lift. So the flapping to equality is literally as the blade comes round onto a faster side, it flaps up, and the very act of it flapping up means that it increases the induced flow through the disc, which reduces the lift on this side, and so we slow our rate of flapping up to the point where we get to a point of equilibrium towards the front. The exact opposite can be seen on the retreating side. So as the blade comes through the 12 o'clock, as soon as it starts to come towards the retreating side, towards the 9 o'clock, you can see we're getting more and more of the effect of the airflow behind it, which is going to reduce that velocity, and we'll have the same issue. But in this case, we'll have max rate of flap down. So we can see from this one as well, that's going to give us the flapping down motion is essentially going to give us a rate of descent flow. So essentially it's going to reduce our induced flow. And as per this side, we've had a decrease in velocity, we've had a flapping down, and our max rate of flapping down at the 9 o'clock point. And what that has achieved is a reduction in the induced flow, and the reduction in the induced flow gives us a shallower relative airflow and a larger angle of attack. That gives us a higher coefficient of lift, which gives us a higher lift. So even though we are losing the airspeed as we come round, and therefore losing the lift, we're also generating a higher coefficient of lift, so it's reducing that rate of flapping down until we hit a point of equilibrium, which will be in this point right round at the 6 o'clock point. Min angle of attack max angle of attack. And we have a minimum angle of attack here because this is where we're going to experience the fastest amount of flapping up and therefore the highest amount of induced flow. We're going to have a maximum amount of angle of attack here because this is where we're experiencing the fastest amount of flap down and therefore the least amount of induced flow. However, we're going to experience the lowest point at the 6 o'clock point where we hit equilibrium and the highest point at the 12 o'clock point. So you can see what we've ended up with is a blade that is not rolling around to the retreating side, but is actually now starting to roll backwards. So we've achieved flapping to equality, but the penalty for this has been flap back. So the important thing to note here, therefore, is that as we start to move forwards, or if we're in the hover and we start to experience a wind speed from the front, we're going to experience dissymmetry of lift, which will create flapping to equality and therefore flap back. And so we're going to need to put forward cyclic on in order to prevent the disc from flapping upwards and increase our movement forwards as required. So that pretty much covers it all. It's quite a short one. You should be able to keep it relatively simple like that. As always, if you've got any points, queries, questions or errors that you've noticed, please just put them in the comments below and I'll get to it.